Can you guys hear me?
Yes,
Cool.
I can.
Yes, I hear you. This is a tab meeting.
Hello, Judith. Hi, Juan.
Nice to meet you guys.
Nice to meet you too.
I hope my talk isn't too boring.
So this is the
No,
tab
no.
meeting, right? This
For
is the
now,
tab
for
meeting.
now.
What was that, Hisham?
Which meeting is this? Ah, Judith. Oh, how are you, Judith?
Good, how are you?
Oh, I'm glad to see you. Finally, you will you accept to present. That's excellent.
It only took like a year of wearing me down.
Excellent, excellent. I'm happy.
Wait till you see the content I present. You might be not be as happy.
This is certainly tab meeting.
Faccio la mamma. Brava.
E lì un secondo, non sono muto. Sì, un secondo.
All right. Great to see everyone here and Happy New Year. So, yeah, let's get started. So Judith, try to share your screen, see if it works. We'll start with a format. Perfect. All right, so let's get started. So welcome everyone to another OCP Tap session. This will be the call number 91. And today we have Judith Olson. So Judith Olson is a PhD physicist working in precision time sources. After designing and building techniques, Judith joined Inflection to bring improved timing hardware out of the lab. She handled multiple government programs to spur the company's research in this area and developed the hardware at the core of Inflection's optical atomic products. Judith grew to lead the atomic clock research group, and she recently moved over to product management to ensure optical atomic clocks coming to the market meet customers' needs and generate new use cases and applications. So today's talk will be basically about the precision timekeeping applications, discussions around that. about around the optical atomic clocks. And with no further ado, Judith, the floor is yours.
Thank you, Ahmed. I'm not a database person. I did try to orient this talk towards applications with a focus on databases and optical networks. That being said, it's not my specialty, so please call me out if you see any critical misconceptions. And I actually have a few questions for you guys at the end as well. So optical clocks, this talk is really designed to highlight some of the main use cases we see where they could have near-term impact on data networks. I'll start out by kind of generally overviewing what a clock is, what an optical clock is, and then how optical clocks could end up working their way into optical networks. And then I'll go into some of the specific use cases related to optical switching. So optical atomic clocks, they work on the same basic principles that all atomic clocks do. If you attended the last OCP talk, you probably heard David Chandler give an excellent talk on how and why and what we're doing with atomic clocks these days. So I'll try to be brief here. But all that a clock really is some local oscillator, so something that's already ticking and counting like a clock. Is somebody asking a question? I can't hear. Okay, it's something that is oscillating.
Just one second, to everyone, please mute your microphone so we'll not have any echo or any disruption. Sorry, Judith, go ahead.
Yeah, no problem. So all clocks start off with some sort of a local oscillator. And this is just an initial frequency, something that's already oscillating or ticking, as you might think of it. The local oscillator for most atomic clocks on the market these days is usually a radio frequency level field or a microwave type field. Some of them use magnetic transitions instead, and optical clocks use lasers. Regardless of what you're using as your local oscillator, the important part is that the signal that gets imprinted on your atoms, the frequency of that is really what determines whether or not you're an optical or an RF clock. So you can use lasers to make a radio frequency or a microwave clock by encoding a microwave signal on the light that interacts with your atoms. That's done a lot in microwave clocks. Does not make it an optical clock. The thing that makes it an optical clock is really that your atoms are responding to an optical signal, so that your atoms are oscillating around at kind of hundreds of terahertz speeds in their states. So you take your local oscillator signal, you have it tuned near some resonance of your atomic transition, you shine your local oscillator onto your atoms, and your atoms will respond to it. So when your local oscillator is right on this resonance frequency labeled by mu naught here, your atoms will very strongly respond. You'll see a big peak in the response there. If you're a little bit further away from it, it won't respond as strongly. And then you can use basic signal processing techniques and loop filters, things like that, to then say, all right, laser, I want you to stay locked to this atomic resonance. So all of that is done by then converting this into an electronic signal of some kind, often using kind of the amplitude of the light coming onto a photodetector. And then this goes into a feedback control system. You generate a correction. And so you're basically taking your local oscillator, poking your atoms with it, asking your atoms, hey, is this the right frequency? Your atoms say, no, move 4 hertz. And then you feed back to your local oscillator and make it move 4 hertz, and the cycle repeats. The biggest difference you're going to see between optical and microwave clocks is really going to be in the counter here. So the counter for a microwave clock, it's all electronic. You are just counting an electronic beat note that comes out of your system or that you're using to, encode onto your local oscillator. If you have an optical clock, though, it's not as simple because electronics can't respond directly to hundreds of terahertz. It'd be great if they could. If those come to market soon, please let me know. We'd be all about them. But for now, we're stuck using a tool called the frequency comb. And so combs were invented around the turn of the century. There's been some Nobel Prizes now related to them. They're really, really useful tools. Their main hallmark is that they effectively form a comb of frequencies. So you have all these discrete, really nice, narrow comb teeth kind of at various frequencies, and the spacing between those teeth is extremely regular. So combs are one of the most magical tools we kind of have in science these days, and they allow us to take the stability of our optical frequencies and down convert it to electronics. So the things that make a good resonance, what makes a good clock, has to do with this resonance over here. And usually we characterize this by the frequency instability, which is kind of silly. It's how bad it is, how unstable it is. So the smaller your instability, the better your clock. And the instability is proportional then to the line width of the transition being used, divided by the nominal frequency at which the transition occurs, and then multiplied by the signal to noise ratio of the system. So for microwave, this new knot, this resonance feature is usually located at some tens of gigahertz. An optical clock, this is going to be located at hundreds of terahertz. And that ultimately means that there's an immediate 10,000 factor difference between these two clocks in performance. So if everything was absolutely identical between a microwave clock and an optical clock, except for the clock transition frequency was moved to the optical, your clock would immediately be 10,000 times better. As cool as it is, that's not how real life works out. It's rare to actually see this full 10,000x improvement, but it does mean that optical clocks are more easily made into very, very precise counters or precise frequency sources to be counted to turn them into clocks.
Thank you.
This is a trend that we've known about for a really long time. So the first microwave clocks go back to the 1960s. The first optical clocks started in the mid-1980s. And again, it's this barrier of having to downconvert the optical frequency that delayed a lot of this. So they used to use these complicated frequency chains. You'd have an entire laboratory space just dedicated to that specific frequency down conversion. And they weren't changeable. You couldn't use it on a different optical frequency. It had to be designed bespoke for the exact clock you were building. Optical frequency combs don't need that at all. So as soon as optical combs happened right around the year 2000, you see a ton of new optical clocks come in. A lot of research was done, and now we have clocks that do surpass microwave clocks by factors of 10,000. They tend not to be the same species. They tend to have moved on to other atomic species. But generally, I'm just trying to show that optical clocks are awesome. We know that they can be better than microwave clocks, and we've been making clocks better than microwave clocks for about 20 years now. And that means, if you're really just apples to apples comparing the average microwave clock versus the average optical clock, the optical clocks can be orders of magnitude better in performance. And this both refers to the frequency instability and then the accuracy. So not just, your clock started ticking, how much did the frequency change? That's instability. But also when you turned your clock on, what frequency was it ticking at? And how reliable was that? And that's the accuracy. And optical clocks have shown the ability to outpace microwave clocks in both of those realms. And then because we have this 10,000 increased factor of instability for the optical clocks, they're also about 10,000 times less sensitive to the environment than the average microwave clock is. So most microwave clocks you buy have lots of magnetic shielding and all sorts of care that has been taken to make them extremely ruggedized, even at the level where you can use them on a card in a lab. Optical clocks don't have to face nearly as many of those barriers. And then optical clocks in the lab historically have been very large, but the fundamental limiter of the size for optical clocks is typically not a large volume. You can fit all of the atoms you need for your optical clock inside of a fixed, cubic centimeter about, or actually much less, but usually for vacuum needs, you need at least a cubic centimeter, which means that the thing that limits the size, like the 5071A, you want that tube as big as it can be. But what David was saying is that 19 inches was chosen because that's the length of the rack. They wanted it as big as it could possibly be. Optical clocks don't need that. So for our same, 3U rack mount unit, our package of atoms is about 2 centimeters long. So they can be made much, much smaller. And when you do that, you bring down the weight. I'm not convinced they can beat out in power yet, but people are working on it. And then the one really cool thing that hasn't been leveraged very well yet is that they can be interfaced optically. So you have stable output signals in the optical realm. You have a comb and a CW laser in the case of most of these clocks that can then be used immediately in the optical without needing electric down conversion. And this happens a lot right now in metrology labs to do just optical beat note measurements, things like that. But it's not really used as much in industry. And that's one area where I've been digging in more to see how it could be used and what value it could bring. So do you have any questions on kind of the clock background before I go into a few more specifics? Okay. So where are optical clocks now? Commercial optical clocks, they're just coming to market. There's lots of room for improvement. The first ones hit the market in the last year from the company I work for, Inflection, as well as a handful of other companies throughout the globe. We're all kind of coming to market at the same time and trying to get these out there. This is the first generation of commercialized products in this area, whereas microwave clocks have had many, many decades and iterations to improve on. The ones that are coming to market now are really designed to be simple and easy, which is a difficult thing for some optical clocks to do. And so we expect the performance here to keep on improving over the next years and decades. Most of the clocks coming to market from the optical clock land are really just designed to act like an active hydrogen laser. So something you currently can buy, but in a much, much smaller form factor and much less environmentally sensitive. So if you ever get the chance to use a maser for an activity, you probably are familiar with the fact that it needs to go on a vibration isolation stage, or at least vibration isolation beat, and then all of that needs to be wheeled into an environmental chamber that carefully controls the temperature to millikelvin and controls the humidity very well. The optical clocks coming to market don't need many of those features. And the ones I'm working on under the Ticker product line label, we've seen operate very, very well in rugged off-roading conditions and all sorts of temperature swings without really needing an environmental chamber. So ultimately now we have clocks that are about the same size as 5071A, but that have performance that can vastly outpace the 5071A. These clocks are not the final tool that will be available for optical clocks. There's a lot that you can do well beyond what is commercially available now. And so these are things that are being worked on. This includes phase-stable optical signals. Just like phase-stable electrical signals are really useful for signal processing and encryption and all sorts of modalities of computing, phase-stable optical signals are expected to provide the same tools in optical signal processing. When you have a phase-stable optical and you get to down convert and reduce all that noise by about a factor of 10,000, you get not just phase-stable microwave, but kind of some of the most phase-stable microwaves that can possibly exist in the world. So these are used a lot in like VLBI and other types of systems. And then timing needs also. You can start caring about time at levels that human perception is not capable of understanding really. So we're talking about clocks that are capable of doing sub-femtosecond timing that are used in the lab. And that's where you have a clock that's in the 10 to the minus 16s at 1 second or better. The optical outputs from these really haven't been explored either. So there's potential for these clocks to turn into a kind of an optical output suite where you could effectively have a little tiny box and ask for any laser frequency you want and get it out of there. And then chip scale optical clocks is another area that's being developed. So we're working on our prototypes here in a modular land. There's a picture kind of what we expect the interior of one of these photonically integrated chip scale clocks to look like. And we expect to have a sub-liter version of this available within the next 5 years based on our current roadmaps and efforts. So they're rapidly going to get smaller. They're going to end up being about the size of Mac within the next decade and commercially available, which we think will unlock a lot of applications. So to be as general as possible for you guys, optical clocks, I think of them as a useful tool. Often to fully get the utility out of this tool, you do have to do an outside calibration. So if you care about timing holdover relative to GNSS, at some point you need to sync with GNSS. So some of the things I'll talk about here are useful tools, but may require an additional piece of hardware or interfacing with an outside reference. One you guys are probably most familiar with is timing signals. Clocks tend to be useful for telling time, surprisingly enough. But these optical clocks can provide, as I was saying before, timing signals far beyond anything available today. So you might be used to worrying about microseconds and milliseconds, maybe nanoseconds. These clocks can support picoseconds and femtoseconds reliably. These clocks are important for expanding your ensemble diversity and resilience. The more diverse your failure modes are, the less likely your entire system is going to go down. And then, the things you guys are used to hearing about, timestamps of data, time interval measurements that might be used for things like a phase lock loop using a pulse per second type system, distance and velocity calculations, or timescale holdover. So clocks, they're great for timing. They're also good for frequency. If you're a math science person, you're aware that those are kind of the exact same thing, just through a different lens. So frequency reference, in this case, we're talking about an optical frequency reference where you can start easily getting, sub 100 hertz precision of optical frequency measurements at a single second. If you're talking microseconds, nanoseconds, milliseconds, you start losing some of that precision, but it's still well below most of the limitations that are used right now in optical systems for data networks. So I'm used to hearing kind of gigahertz as being very narrow for a lot of the optical applications and optical networks. And we're orders of magnitude better than that. So even if this gets worse, you want to measure things faster, you still have a lot of overhead. The frequency comb that is built into these allows you to then also kind of measure any optical frequency within the range of your comb. And the comb it's typically at least octave spanning. So it usually at least goes about, a micron or 1,000 nanometers in its spacing. And then these are also very low noise precision electronic frequency references when you do that down conversion. And that's really useful for monitoring your frequencies or doing a frequency discriminator to have a feedback system of some kind. And then when you get even more down into the dirt on this, you can think of these clocks as being a phase reference as well. So again, not all of the phase reference applications here apply to the existing commercial optical clocks, but they are things that are being worked on and expected to come to market soon. The big one here is going to be low phase noise or phase stable optical signals, and then these ultra phase stable radio frequency signals that you might want to use for synthetic aperture radar or applications like that. And then there's a lot of interference-based modalities for compute processing that can use this as a phase reference. So we'll see this both in the optical and the electrical, and having a phase-stable reference that can be disseminated ends up being really, really important for actually, doing your computation and being able to communicate it somewhere else, let alone doing a distributed computation. So there's a lot then in optical data center needs that overlaps with the tools that these optical clocks can provide, both for within a data center for very, very short lengths of fiber that only may go a few hundred meters or less, all the way through kind of the long haul inter data center connections or the metro networks that would use these. And this is in part because there's a drive right now to reach kind of petabyte per second capacity per fiber that is expected to be needed in the next decade. And so if you just do a basic calculation of this, if you assume about 50 gigahertz channel grid spacing as a common number that's used, you're getting about 100 gigabaud rate on it. You need about a 2000 nanometer band to fit all the channels needed there. And the fibers that exist do not have 2000 nanometer broad transparency region that's useful for this. So something needs to happen. We either need to, increase the data rates. This is being done right now with optical switching and some other tools that allow you to send faster data. And then increasing the channel density is the other route. So if you can reduce the 50 gigahertz spacing to something smaller, down to gigahertz or sub-gigahertz, you can start using more channels per fiber. It's complicated to do that. I'll dig into that a little bit later. And then the other area that's being worked on here is also increasing the transparency range. So using things like hollow core fiber or specialized dispersion features in your fibers to help this. So optical clocks, it seems like there's a lot of overlap here. We think they have the potential to improve both data rates and to reduce the channel spacing. So kind of two different ways we could attack this problem of needing to send more data faster with less latency. And then we think clocks cannot just provide the solution, but they can do it in a nice way that ties into the existing hardware used in optical networks today. So, you already have thousands and thousands of miles of fiber out there. It tends to be single mode fiber, which doesn't have great dispersion properties, doesn't have a large transparent region, but it's already there. So if we can find a way to leverage the existing hardware, the existing amplifiers, and all the optical components that are in there, it makes it a lot easier to transition over. And it looks like there is a high level of compatibility there. I'm still digging into details, but I have not found anything that makes me think it isn't possible at this point. Another great need in optical networks these days has to do with the flexibility of the architecture. So you need to be able to redo the paths that are present. If there's a lot of data needing going from one city to another, you might want to take some of that capacity and allow it to ensure that data gets there. So you need to be able to reconfigure your network on the fly. And optical switches and many of the abilities of the optical sync that come from these advanced clocks should enable that. And then some of the existing tools that are used for data aggregation, clock data recovery or phase caching methods can also really benefit from improved clock references. And then this future-proofs the network to some extent. These clocks have overhead in terms of the performance for what we need now versus what we might need in the future. And so by having them integrated into your network, you've got room to grow before you need to replace any hardware. And then for some of the optical networks, there are synchronization needs there as well, or time stamping. So it can also provide those. So basically, that this is new tech. It's scary to adopt new tech, and really we see this inserting in kind of two main areas first. One is where there is no other solution. You need picoseconds for whatever reason, or you need a comb for your system to work, and it's the only solution. And the other one is where it's a high cost system. So anything that requires adding or replacing lots of fiber length or drilling new holes or having to develop new infrastructure is generally very costly. And that might be a case where the optical clocks could really provide the benefit at a much lower price point. So ultimately, this means we think it's really going to give the return on investment to people who are doing either really long backhaul services where capacity needs to increase greatly, or else kind of within a data network itself, intra-data network communications, where you really care about reducing the latency. And those are kind of two separate but parallel paths to improving the data rates that can be, or to improving the data communications that can occur. And we think clocks can attack both of those. So that's where we expect them to start showing up, these optical networks. And as they become more ubiquitous out there and they become networked, we expect a whole other host of applications to appear. So the availability and maturation that will occur from optical networks will enhance these future needs. This will include embedded local timing for things like increased asynchronous time transfer over long haul, where you might normally need to include a timestamp. You might not need that if you can have better timing. It can also enhance some of the aggregation techniques through time division multiplexing. There's even been some talk of trying to clock computers and CPUs at higher rates using signals from very stable optical clocks. And once these clocks are in the network, if you reference them in any way, shape, or form to UTC and then have holdover, you also then have a backup network for GNSS type applications. So anywhere where you might normally use a GPS signal to get a sync operation, you're at risk of losing it. A volcano could go off and block satellites. There could be a horrible incident in space that causes satellites to go down. You could be in an urban canyon or want access while in tunnels or things like that, where you just don't have access to satellites. This could act as a resilient backup network for that. And then there's a lot of modalities for optical communications, optical signal processing, and encryption, particularly post-quantum cryptography, seeming to lean into many of the techniques that come out of precision optical sources. And then the last one here is near and dear to my heart, some of the future quantum networks that are being worked on. So a quantum computer, it's hard to fit a lot of bits in a tiny area. Eventually, you need to have kind of two separate quantum computers, and you divide the computation up between them, a lot like what gets done with data centers today. That means you need to communicate between those different quantum computing nodes. And that becomes very difficult, and it becomes extremely time sensitive. And as researchers have dug into this more, they found that you are going to need picoseconds and you are going to need femtoseconds for this to be done reliably and to allow for long distance quantum communication and cryptography. So having all these built in already could make these networks very future proof and enable a whole host of other useful applications. Are there any questions about that before I dive into optical switching specifics?
One thing is, just wanted to add also, I mean, I think you also mentioned it, but just emphasizing more is when you introduce like these like clocks, let's say optical clocks, you increase the number of nines in terms of reliability. So that can be also an important, let's say, application for the type of work we do. Like you want to have in data centers, again, more reliability.
Yeah, absolutely. Okay, so for some of the optical switching applications we've been looking at, the more conventional switches used in optical networks are where you have a light input, you receive it, you have to convert it back to electronic levels, where switching might occur on the nanosecond or kind of gigahertz level if you're doing it really well. And then you have to reconvert it back into optical and send it out. This is a fairly time-consuming process. This is fairly power-hungry, and it's inefficient overall. You waste a lot of power by having to go back to the optical. So there's a real push lately to work on all optical switching modalities, where you have optical in, you do your switching itself in the optical, and then you have your optical coming right back out. This can be a lot faster and less power-hungry than electrical-optical switching. So we're talking here now, picosecond timescales or terahertz type processing speeds. As you do this, as you're able to switch faster, you often then need better timing for it. So the most strenuous things are going to be at the bit level processing. This is going to be the all optical processing, all optical switching that can be used. But the other levels of communication also need really good timing. So packet switch compliance, you're going to be talking about nanoseconds and gigahertz type levels. It's really important for all of the multiplexing and data traffic routing. And then the slowest one here is the reconfigurability of the backbone. And that's just because this is inherently a larger inertial process. It takes more computation to understand how you want to reconfigure your network or anything along those lines. So usually those changes occur on kind of the millisecond level. So we are thinking about then the nanosecond, picosecond kind of levels of switching that's needed here. We think clocks have something to offer there, especially these optical atomic clocks. This comes in both from vastly reducing the timing jitter on your signal production, as well as improving the reliability of your timestamping or your data packets if you have a very stable source. And this also can enable bit level high-speed processing when you have the ability to use these optical switches and stable optical signals you trust going into them. And then the reconfigurability of the backbone, this is also addressed with optical clocks, and in part through the wavelength selective switching, or the potential for these clocks to act as multi-wavelength sources. So the wavelength selective switching is another aspect of these clocks, where if you want to have, 50 to however many thousands of channels of different wavelengths in a single line, you need to be able to split them back apart and individually change the properties of a specific wavelength channel. This is usually done these days with MEMS or liquid crystals. So the most conventional method out there that I've seen is MEMS, where you use a basic diffraction grating. The diffraction grating will reflect light off at a different angle that depends on the wavelength of the light that is incident on the grating. So by using an array of fibers, a diffraction grating at a fixed angle, and then a mirror, you can route things into a specific output fiber of your choosing. And this allows for wavelength switching to occur. Usually 50 gigahertz is a common spacing I've seen here. Somebody ask me a question.
Sorry, can you guys please mute your microphone? Like, still have like some noise.
Sorry, if you were asking a question, just keep trying.
Yeah, all for you guys are still
Okay, so the channel spacing here, though, is pretty limited, in part by the gratings themselves, in part by some of the limitations of the fiber or the optics going into it. But typically I've seen, some 100 of different wavelength channels that are possible in a single fiber using these MEMS-based wavelength selective switches. They have really good extinction ratios. They were able to scale pretty readily. So these spread, from what I know, pretty nicely throughout the optical networking area. They can be arrayed heavily. They do have quite a few downsides. They require very high voltages to operate. There's a lot of optical aberrations that occur when you're using these strong angles. And then there's crosstalk during the switch. So in order to get from, for instance, on this picture, from the top fiber to the bottom fiber, the most direct path is a straight line, which would temporarily couple your light into the 3 fibers in the middle. So that there can be crosstalk during that. And then maintaining alignment on these systems is really difficult. Most of them seem to require some level of active feedback or recalibration period, which is time consuming. It means you can't be using that node during the alignment period. The other 2 methods that I found are really based on liquid crystals for the most part. The simplest one is this binary liquid crystal method, and it really just divides the light into its 2 orthogonal polarization components. So it's a 1 to 2 switch. If you want to do anything more than that, you need to start stacking them, and that does not scale well, both from the distortions in the beam profile and the power losses at each stage there. So every time you go to implement one of these, it's great if you're doing something small and just need a few different switches. It's hard when you want to integrate it at kind of the full network level, though. It also means it has high overhead, and it's not fun to use. You often need additional amplifiers or beam shaping techniques afterwards to really make this work. That being said, it's probably the easiest to set up initially from what I've read about it. You don't really need active feedback for alignment. It can be misaligned and still work. The best channel spacing I found from these types of systems gave about 12.5 gigahertz, which is a little bit better than the MEMS, but still a lot of room to go, I think. And then the most advanced one here is this liquid crystal on silicon, or LCOS. This is essentially a phased array, like what is used in many optical heads-up displays or systems like that. So you can very, very carefully, by having lots of little tiny mirrors, kind of chunk up your beam into small pieces and then reorient them to change the overall phase profile. And so by adjusting the angle of those little tiny mirrors, you can make it so your beam actually points in a different direction. The really great thing about this is it also allows you to reshape the beam while you're doing it. So you can have intensity control effectively. If you have some, high input system that initially needed a lot of power in order to do some processing level, but you want to couple into a fiber with a small amount of light, you can intentionally reshape your beam without needing a specific intensity-based controller as part of the liquid crystal setup here. It can also be configured dynamically. So this is during operation. You can change exactly, what the coupling is between any 2 nodes on your system, and it seems to work really well and be very fast. However, it's more complicated. Each of those individual reflection surfaces needs to be individually controlled. It's newer. It doesn't seem like it's as mature of technology. That being said, some of the companies working on this have said they can get down to 1 gigahertz resolution on their channel spacing with this method. So it seemed to be the narrowest channel spacing I could find in terms of systems out there. So you'll notice all of these channel spacing wise, though, they're still in the gigahertz range. And we think we can do better. There's lots of reasons why people haven't done better. I'd love to hear more from this group, especially if you have other ideas. But at least from what I could find, it didn't seem like there was a reason why you couldn't go down to 100 megahertz or narrower spacing right now. Optical clocks often use a frequency comb that has 100 megahertz spacing. There's some where you can get gigahertz or tens of gigahertz as your spacing. But the 100 meg would give you the highest channel density. I understand it's complicated by a variety of reasons, but if you also have this comb very well referenced to an optical clock that is very stable, at the very least, I would imagine you could reduce your guard bands. You know exactly where that frequency is going to fall. You know exactly when to look for it. And so maybe you don't need as much spacing between all of your frequencies in the different wavelengths. And then there's a lot of physical limitations that come in just from the transport layer as well. So optical aberrations, laser line widths, amplifier line widths, dispersion, diffraction within the fiber itself. There's all sorts of things that can come in, and they seem to be fairly dependent on the use case and the length of fiber needed. That being said, we've been looking into this a little bit, and it seems like there's some meat here to dig into further that could let us go down to this 100 megahertz spacing. And this would employ a combination of techniques. So it would use the physical separation currently done for gigahertz spacing, and then apply both the CW absolute frequency accuracy from the clock with the comb teeth, and then some filters and photonically integrated circuits that seem like they could allow 100 megahertz spacing. So you could have, you know, whole comb of frequencies going into your photonic circuit. You can then divide them up and filter them. So each individual comb tooth has an output layer. You can then process optically however you want, and then couple them back in and send them back out. So it seems like this is a potential way forward to increase your channel capacity that we're looking into. So ultimately, you know, it depends on where your starting point is, but this could increase the channel density by anywhere from a factor of 10 to 500 based on where your starting point is. And then there's one other application that came in. It seems like in some levels this has been solved, but if you're still sticking with single mode fiber systems, it is still an issue. This has to do with, you know, wanting to reduce the latency that comes specifically from the clock and data recovery circuits. So serial data communications, you send all of your bits through your system, and then you apply the timing information afterwards. This can be a fairly complicated process based on how poorly aligned your system is and how much the phase is changing along your fiber. But generally, you know, it was found to be a dominant latency mechanism, particularly within a data center that is using optical processing. So Microsoft found that CDR actually dominated the latency in many of their different data centers out there. Most of their messages were really, really short, but each time you sent a message, you had to redo the entire clock data and recovery process. So it ended up being really time consuming, taking up, you know, I tried making a pie chart of this, but it was almost all clock and data recovery with really tiny slices for everything else. So I went back to just listing it. They found ways around this. However, phase caching is a really nice way that seems very effective here. And this is where you kind of track the overall global phase difference that's needed between the timing information coming in and where you're actually doing the sampling. And then on top of that, they found they could reduce any of the need to remember the phase by keeping it constant by going to hollow core fiber. So there's a hardware solution. If you just switch everything you're doing over to hollow core fiber, you can reduce a lot of these problems. If you want to still use your legacy single mode fiber though, clock data and recovery along with phase caching is a really nice way forward. And the phase caching that is used is fairly dependent on the timing jitter on your signal reference. And so if you have a very well-referenced signal to start with that doesn't have a lot of timing jitter, and you have a really nice receiver on the other end that you trust to stay in sync, the need for phase caching could be reduced. So you might not need to phase cache as often, or some of it could even be eliminated. So basically, there's a few different ways forward with clock and data recovery, but we think it still could be beneficial, at least for some of the various modalities out there. Okay, so those were general applications. Are there any questions on the content I presented before I start posing some questions for you guys? All right, that means it's quiz time. So one of the questions I came across was that I've been trying to understand what really determines kind of the shortest possible signal that can be sent. What is the shortest way you could represent a bit? And it wasn't entirely clear to me why or what is causing those to have that finite length. Obviously you need a finite length, like they're a physical signal that's being sent, but why aren't they shorter? Why are often these having many nanoseconds or longer for the signal for each bit? And I wasn't really sure if this came from time broadening or it was a modulation bandwidth limitation. Does anybody here have some feedback on what could be leading into that?
Modulation problems are detection problems. So, yeah.
It's both?
Yeah, no, modulation problems are detection issues. So, it's very difficult to integrate, the result of your observation over some amount of time. So you have to allow enough time to be able to make a reliable measurement. And so that is kind of a kind of a laws of physics pushing back a little bit on modulation rate,
Okay. And then does it also have to do with kind of alignment of the timing between when you sample the signal? Like you need to verify you have it at some point and then sample within the middle so you don't end up getting bit errors.
You sample it asynchronously. That has been the argument we've been like making here. It's like if you can measure it, it's not jitter anymore. So
yeah. Cool. Okay. And then are all of these generally, if it's in the modulation, it's built into both the long haul and intra-data center. So it's not really specific to one area of the network. It's a more global problem. Is that correct?
It's a peer-to-peer problem.
Okay.
Peer-to-peer applies everywhere.
Well, yeah, I mean, there's different, link budgets, right? For all of these different optical techniques. And so these different link budgets are kind of like there's not a Rosetta Stone, if you will, that will help us to go between all these different link budget problems.
Okay. Thank you.
Anyone
and
add anything to it? Sorry. Let's go forward. Sorry.
Okay. Another question we have is these clocks have options to have optical outputs in telecom C bands. Some of the other optical clocks out there can address some other bands. Generally, when talking to people doing optical networks, though, they don't seem very interested in having a very stable output frequency there. And I wasn't sure if this would be a useful reference for instance, some of the wavelength switching that's going on. I see them jumping between two different wavelengths. In theory, you could use this to reduce the time it takes to settle between for instance, a DBR switching between two different wavelengths. Is that something people care about? Is that useful?
I wish I had my optics people here.
Could be interesting for if you had a coherent modulation technique, because this would allow really a good source to demodulate.
Yeah. So a lot of this seems like it could be fixed by just doing a phase lock loop or frequency stabilization to an existing reference with a fixed offset. And it sounded like the settling time was some number of tens to hundreds of nanoseconds. And that if you had a reference, I'm used to seeing some of these phase locks occur very faster than that. So that could reduce some of the time it takes to actually switch between, a 0 and a 1. And then I wasn't sure if what level of calibration or characterization is even done of the wavelengths being used. When you're dividing things into wavelength channels, how careful do people need to be? Do you care if there's an offset? Do you care if there's breathing between the channels where they're kind of all moving apart from each other? Or is that just carried in the guard bands and,
depends on the
problem?
It depends on the phi. I mean, because, different phi techniques require different levels of jitter and, frequency, I guess, stability. And so that's difficult to answer. I think you have to look at each different phi and answer it separately.
Makes sense. And then for reducing the gate or the spacing, the channel grid spacing further, are there any other issues that I didn't touch on at all that this group might be aware of that stop this from being possible? It seems like the spatial separation is the key to making this viable.
One of the things I would worry about is something that's recently been verified experimentally, and that's something called indefinite causality. I just put a link in the in the chat. This is the work that's done by Julia Rubino, who I'm sure you know, and also the original theoretical work was by Kaslak Buchner in the University of Vienna. So this indefinite causality idea basically says that, you know, space-time is not a smooth background. There is something else going on here that we have to account for. And at the moment, that might look like statistical variation, but there may be, you know, something interesting new physics underneath that.
Yeah, that would be cool. One of the other less data center oriented applications we've looked at for the clocks is kind of just using fiber networks to assess what's going on in the world. You can start doing earthquake detection, early landslide monitoring, things like that. Because the path the fibers take is not perfect. I think you're probably hinting towards more interesting physics there, but that'd be cool to look at too.
Well, one of the challenges that we're looking at is how we can use timestamps and whether or not they're useful, because you know, any timestamp against an inaccessible background, whether it's Newtonian or whether it's Minkowski, is not going to be accessible. Whatever you get in your registers is going to be some kind of you know, epistemic, you know, thing you can measure, and not necessarily what's going on, you know, in the physics of space-time. And so the big question is, you know, going to a shorter and shorter resolution on time, going from milliseconds in NTP to nanoseconds in PCP, and then now to femtoseconds and attoseconds. You know, where does it stop? We call this sharpening the guillotine.
How sharp does it need to be?
Well, all that happens is you reach a point where your variation because of space-time intervals, you know, from different arrival order from different parts of the data center network are just going to, you know, completely swamp whatever accuracy you're given for the timestamp. And so we think that looks like, you know, these clocks are incredibly useful, interesting things, but the obvious use of timestamps doesn't appear to be as straightforward as we thought. For example, you know, we know with great certainty that you can't construct transactions out of timestamps. Okay.
I think that is definitely it's a concern with the clocks we build right now too. You can start measuring gravitational redshift over distances. At least the clocks that we're building now, they're not quite good enough to do that. But you know, just up the street, Juni's able to measure, you know, millimeters of change in the height of their atoms caused by the redshift. So that's a really good point. It's going to get progressively more difficult to actually utilize and communicate and find value in having timestamps at those levels.
Yeah, I was teasing Ahmad the other day that this is really this should be the quantum sensors group, not the TAP group. So
it'll evolve that way naturally. I think get this right.
So one thing I mean, thinking practical about these things is when you look at like channel capacity, we rely heavily on the eye chart. We want to keep the eye open, and I mean, I might be wrong, but like when I have such an approach that I'm looking for the eye to stay open, this is basically a asynchronous method that like I'm trying to recover the clock back from the adjustment of the signal that I am getting on the same thing. Because again, I mean, it is what it is. Like there is no separate line to provide me the clock to have a synchronous thing. I mean, think about it like how you have, let's say, UART versus USART, right? Like in the USART, which is the most popular one, you have the TX and RX. You have just one signal, let's say, in each direction from the signal that you get the data from. You're recovering the clock, and then ongoing as you go, you start using this clock that you recover to do your sampling and you recover your bits. So the same thing, let's say, applies here, where at all these crazy frequencies and everything that we're getting there. I mean, I don't think our SerDes, again, I wish there were optical peoples here, but I don't think our SerDes are getting anywhere. I mean, last time I looked into this, we're still at 25 gigahertz, or, I mean, Bijan, you can help me. We're still at 25, but we went to 50.1 or something like this, 51 point something. And we're still there. And then while we say, oh, we are like QSFP and then OSFP and then whatever SFP, like we keep like just putting lanes in parallel, and we're basically like, you know, making our way through 800 gigabit per second. Well, like it's a bunch of 50 or 25 lanes that you just keep cramming more and more of them. And then at some point you run out of like that space, and the connector is like already so big on the OSFP, and then like, we keep like doing this, right? But then at some point we reach this limits, and it's like not so practical anymore. And then, I mean, expanding, like this is like a horizontal expansion. Then we look into, and then this is traditionally what we've been doing. Then we start looking into wavelengths. Oh, let's put a bunch of like, I don't know, multiple like wavelengths on the same thing, and have, again, this is what you're mentioning, the spacing between them. But this is where things start becoming interesting, cramming more in frequency and cramming more in time, right? In frequency, again, you need to account for the fact that this, like, I mean, we use this OSFP, QSFP, whatever, these form factors. You don't have them. I mean, it's very difficult to have them, let's say, temperature compensated. They're like a little thing, just stick it there, and then, I don't know, 18, 30, I don't know, 20, 30 something watts consumption, and usually some passive cooling or active cooling, yeah. I mean, just some heat sinks, and there's airflow, and you go through it. But the temperature changes, they will, I mean, change like the dynamics of like the transmitters, I mean, also the receivers, and then the frequencies will shift. So you have to account for all of these things. That's all valuable traffic that you're losing, you know, like you can use all of this. Again, this is in frequency domain. In time domain, again, we rely heavily on that eye to be open. Imagine if we were, I mean, I'm not saying like, oh, we can do something if the eye is closed, but then we can really have, for less SNR, the capability to detect things. If you know precisely when you have to run your assessment and your threshold, and then exactly at this time, you know, like, and then in let's say picosecond or something. And if you want to get to that point, you need your synchronization basically on the two parties, precise enough. And you want to have precision on this, on the synchronization. You need to have both parties to have enough holdover, or let's say the ability to maintain the time, because you are at some, again, when you go down, I mean, synchronization, you always are fighting with entropy. You need to have the entropy brought down to the minimum to have the assumption of the stability of the two sides. So then the T1, T2, T3, T4 method will perform the best it can with the two assumptions that it has, that both sides are stationary and you have, let's say, symmetry. So I think with that in mind, you, again, like, I think if we can have an application that really translates directly, like, hey, your clock getting, let's say, 1,000 times better, let's say 1 to 1, let's not 1 to 1, like a 1 to 10, let's say, that, like, if your clock gets, like, let's say 1,000 times better, your throughput for the channel gets, like, I don't know, 100 times better. You will have an extremely selling point, because we are reaching a point that, let's say, if you have, because it's a compounding thing. Right now we have, let's say, I don't know, terabits of connections, like over a fiber going like in the ocean. And who doesn't want to have, let's say, 100 times more throughput on the same thing, you know, like, because your main cost is there.
Yeah.
So, I mean, this is the ultimate thinking, like, here. Like, again, if you have the two parties, again, and this is coding you, Judith, you can have the best clock in the world, but not correct. So you need the synchronization. It doesn't matter. You have the best clock there, fine, but you provide the synchronization.
Clock on its own doesn't do much other than let you know it's ticking.
Yes, exactly. Just the steadiness, just reduce variance.
Okay, and then the other questions are, you know, are there other features or things you guys could see? Are there ways you might want to use this tech that I haven't thought of, where, you know, this would be great if you added this one thing to it? And then also we're always looking for collaborators and people to try to test some of this with. You know, as simple as, you know, seeing how bad it is if we try to go down 100 megahertz channel spacing would be a really nice starting point, so we know what we're fighting against and how good those filters really need to be.
Well, there's a couple of things that I'm aware of in the quantum computing world. You mentioned earlier on that quantum computers really are dual computers that are connected by, you know, a quantum network. One of the things that we'd like to be able to do is, instead of assuming that there is some clock ticking against some continuous background on both clocks either side is to say, well, hang on a minute, if one of them needs to adjust relative to the other, that's a causality violation. And so having a protocol, for example, that can recognize then one clock is slightly slower and therefore the other clock needs to adjust, you know, that's actually a really important piece of information that I'd like to put into our algorithms.
So that's pretty easy to do in the optical realm. Like for the case of two optical clocks, you could basically just have a beat note measurement go along. And when they're perfectly in sync, it's in sync, you see a 0. And when one starts to drift, you start seeing, you know, a beat note appears. So at least optically, usually I've seen that be a pretty fairly straightforward mechanism to implement, even over very long distances of fiber. And it accounts for the changes in the fiber as well if you implement it correctly.
But that sounds really interesting, and then certainly there's going to be a lot of temperature and other variations that happen in the path, which if you can account for those automatically, that would be useful. So my question to you, though, is how long does it take you, would it take you to distinguish that beat variation?
It would depend on the signal to noise of the beat note, so how much light is being coupled in. And ideally, you'd offset them. So the further away from DC you can measure, the better your measurement will actually end up being. So if you're trying to measure a change from DC, it's not great, but you could intentionally offset your clocks by however many megahertz and then measure that beat note. I imagine you could see it pretty quickly. You know, we can tell resolution far below what typically is used in the optical. So we can start seeing hertz level differences in these clocks pretty readily.
So hertz level differences at terahertz?
Yeah.
Okay, I get it. All right, so that's really interesting, and I'd like to figure out how I can use it. My question is, when you measure this beat variation, that's going to give us a trigger, which we can then say to the algorithm, okay, can you know, this just happened. One clock is, you know, which was, you know, ahead is now causing the other clock, which was behind, to catch up with it, or vice versa. And so one of the things that we're interested in is this this handshake between beat variation happening on both clocks, for example.
Yeah. I think that would be something that we'd be interested in you know, talking about more and understanding how it could actually work out. Usually, I'm used to using these kinds of locks and servos in, you know, fibers, so we can make sure we're measuring our clock right. Because if that fiber length is changing, you're going to see a phase variation, and you know, you won't actually know what your frequency was relative to the time scale. Most of those seem like they apply pretty straightforwardly to these optical applications and networks. It seems like there just hasn't been good communication between, you know, hardcore academia and the people actually building these systems in the real world.
Thank you.
Yeah. I think that's the end of my blathering, but my email's here. Please reach out.
Yeah.
Yeah.
The one more thing, like I want to mention, like this is something we were discussing with Paul actually last week, which is like the synchronization that we do, let's say today, like with PTP and everything and so on. I mean, synchronization is a little bit misleading. I will say the term is more tracking. You're tracking one clock to the other one with a numeric method. You just measure, you do some measurements. It's all like, I mean, nothing is perfect, and you go through making one clock track the other one.
Yeah.
Trace. Something, again, I speak from ignorance. I don't know that much about the specific. Is like, let's say if you have optical clocks, or let's say if you have, again, this is just from optical clock, I dare to even question this perhaps. Can you combine that with, let's say, quantum key distribution, and you have a source, instead of you sending like basically sync messages, you're sending basically the split of photons, and then you get basically on the two physics chambers entanglement that you create now the clock. Again, you can, I'm assuming you will have entangled provided, let's say, frequency generation. You still need a sync, and then you provide the sync, let's say, with a numeric way, but then you're having an ultimate holdover here, because you're for real having two clocks. I mean, it's still an open loop from my control perspective. Okay, it's not a closed loop, because you're just sending on the two sides. And the moment you want to do the closed loop, the closure, you are getting back to all this imperfection. But at least the chambers are entangled, and then you run the things, and I think you will have a next generation, like of performance in time transfer.
So entanglement is used a lot in time transfer right now. It's very similar to quantum key distribution. There's a handful of companies working on this, both the United States, the UK, and globally. You can use this for, I think the best numbers I've seen are tens of picoseconds in terms of the time synchronization that can be provided by this. But there is a push to include this in clocks. It only works with some kinds of clocks. So the clocks that we're using and the photons we use to excite it, it's a non-coherent process. The clocks, the atoms don't care what phase your photons are, what phase your light is, or anything like that. And where you seem to really get the benefit with entangling clocks are situations where they do care about the phase. And that means you can reduce the phase noise and quadrature if you interact with them at the exact right time. So at least the clocks that are coming to market aren't going to be capable of being entangled, I don't think. But future clocks will be. And entanglement modalities for time transfer are already out there. And so if you can use that same time transfer photon system to entangle your clocks, you can also then get better performance from your system, especially if you then line up that with your readout pulses. So you can choose to read out only when your phase is optimized. So
yeah, that read has also another problem again. Like I want to just, for reference, bring it up. It's like, again, you get stuck with the same problem that you mentioned. Electronics cannot get you, beyond, let's say, tens of gigahertz or something. Then you want to do the sampling. You have to also think about the sampling done in optics, somehow.
Yeah.
To really take advantage of this synchronization. It's you have, like, let's say, sub-picosecond synchronized two parties, and you want to send something in between. How do you want to do the sampling now in a way that you utilize this sub-picosecond, precision that you have at the two ends? Electronics cannot help you with that. So,
I mean, there might be ways you could do it by interleaving,
it's probably interleaving,
or things, but it's going to be complicated fast.
But it has to be an optical method, I'm assuming.
It could be optical, but you could do something in optical and then kind of store the information to be retrieved electronically when it's ready.
Yes, of course. When it comes down, you turn into electronics.
Yeah.
I think that the challenge is that the scales are different, right? So to achieve what you're suggesting about is, we're talking about single photon detectors. And so the scale of mass, optical today it's much higher. So I don't think you could have a precision that would be meaningfully better than what you're doing today, using that kind of approach, until you go to single photon detection, right?
Yeah, that's what I'm used to seeing with most of those QKD type distribution systems.
Yeah. But it's an interesting thing. Like, I was thinking when you were talking about that, to have, let's say you had two entangled spaces, one at each end of the cable, and then you rotate spin or something on each electron on one side, and then the medium in between transmits these differences to the other end. It's a different kind of modulation.
That could be interesting. I'm not sure how you. There's a lot of cool things you can do with entanglement, but it's hard to actually get something useful and measurable out of it.
Yes.
I'd have to think about that one more for sure.
All right, we are on top of the hour, and is there any more questions?
Thank you. It was a great presentation.
Oh, thank you very much. Appreciate it.
Yes, thank you. That was really wonderful. I enjoyed it.
So if there is no more questions, again, on behalf of everyone, I want to thank you, Judith. And we'll see everyone in 2 weeks by talk from Greg Armstrong about Let's Talk Servos. So again, Happy New Year, and enjoy the rest of your day and rest of your week. See you in 2 weeks.
Thanks
Bye,
very
everyone.
much.
Bye.